So this next section of integration deals with what we call improper integrals. And these are integrals that you're not allowed to invite home for dinner. You're not allowed to go and hang out with on the weekend. They are improper integrals. And what we mean by improper integrals isn't necessarily that there's anything actually wrong with them per se. But to address this word improper, we first need to remember what integration is. And integration, at least integration that has bounds, we'll say, right? An integral from, say, a to b of some function f of x dx means that I have some function like this, f of x, and I'm integrating on some fixed interval from a to b. And visually, we've spent many videos discussing, that this ends up giving us, visually the area under the curve. It also, has a more practical application in that integration literally means to add up a whole bunch of tiny things. We've talked about work. We've talked about arc length. We're going to shortly talk about probability, right? We can add up all sorts of different things. There's a bunch of different applications of it. So what exactly makes an integral improper? Well, there's two sorts of things. And there's two kind of situations that we haven't yet tackled. And the first is, we know how to do this if our region of integration is what we would say finite. That is, if I were just integrating from a to b where both of those are real numbers, no problem, right? Obviously, I'm going to be able to get some numerical answer for this. But a slightly more interesting question would be, what if I had a function that kind of is super wily and kind of goes on kind of unpredictably forever and ever and ever. And I also, for whatever particular reason, wanted to, do an integral from, say, the number 3, or actually, let's just keep it simple. Let's just say 1 all the way to infinity, which, visually would mean, right, that I'm trying to calculate the area underneath this function for all eternity. Okay, now the applications thereof, they kind of vary, but just for now, just imagine that we're going to learn how to deal with this technique, which is, what happens when we replace one or both of these bounds with something that looks like this, right? What if we have an integral that goes from 1 to infinity? What if we have one that goes from negative infinity to 7? What if we have one that goes from negative infinity to positive infinity, right? What do we do, right? How do we even begin to talk about adding up a whole bunch of stuff on an infinite interval? And, the process, it turns out, to do this is actually very similar to what it is we've been doing. It's going to require a little bit of Calculus 1. But I'd like you to think about why this is an issue in the first place, right? Just imagine that I pop this question for you, right? I want you to integrate from 1 to infinity. Okay, now, on the one hand, you might say, well, everything that we've done says that I'm going to, at every single x value, I'm going to be adding up infinitely many tiny rectangular areas, and I'm going to do this for every single x along, between 1 and infinity. And if we do this, you might say, well, there's infinite space over here. So on the one hand, you might think that this answer would naturally be infinity, right? Based on this drawing, say, hey, there's infinite space, no problem, right? The answer is just going to be infinity. I'm adding up infinitely many rectangles, and not only, we added up infinitely many rectangles before on a fixed interval and said, okay, well, this kind of makes sense that since these rectangles are really skinny, right? They're really, really tiny rectangles with a width of dx, that if I add them up in a finite range, okay, sure, I buy into the idea that I'll get a number for the area underneath this curve. But for an infinite amount of space, right, adding up infinitely many of these things, you kind of think about it like grains of sand on a beach, right? If I add up infinitely much sand, I'm going to get an entire beach, right? I'm going to get everything. So thinking that the answer is going to be infinity is not a wrong thing to do. But imagine, now that we have a function that maybe, looks like something that you've seen before. What if I have a function that kind of does this, right? And then let's say, like, in the long run, it kind of dies out. Okay, so we're going to say, like, as x approaches infinity, we're going to say that my function, the y value, approaches 0. Okay? And so we're going to say, let's say, again, from 1 to infinity is all the way out here, that in theory, all I'm asking you to do is calculate the area under the curve. But notice that, this area kind of starts to diminish over time, right? It gets smaller and smaller and smaller and smaller and smaller and smaller, like so. And the question is, the real big math question is, can we still add up infinitely many tiny rectangles, to get a concrete number, right? To get a concrete number. Okay, can we still do this? If I draw my little rectangle and I say, there for that particular x, is it possible if I do it for all the x's from 1 to infinity, is it possible that when I add up all of these rectangles that I don't get infinity? Okay, and this question that I'm posing to you right now is actually a cornerstone of where you will start in Calculus 3, and it's this idea of that if we can add up a whole bunch of stuff, like I said above, we've already, entertained the idea that here I'm adding up infinitely many rectangles, right? But the answer is not infinity. The answer could be like 7, right? The area here could be 7 square feet or something like that. Like, we've dealt with problems where I could add up infinite amounts of something and get a finite answer. And here, you never really thought about it because you're like, okay, A and B are finite values, right? I'm adding up infinitely many rectangles, but I'm only doing it on a finite region. So, I buy into the fact that I'm just going to get some number out. And the idea kind of translates to this really well, which is, again, sure, we are adding up, infinitely many rectangles. Okay, we're adding up infinitely many rectangles, but instead of doing it over a finite range, now we're doing it over an infinitely, maybe I should write that out, infinitely long, domain of integration. Domain of integration. I'm not doing it from A to B, I'm doing it from 1 to infinity. And so the idea is that, whereas before, these rectangles could be any height, right? We said those rectangles could be any height, and the theory says that I can still add them up. I can add up this one, I can add up this one, I can add up this one. It doesn't matter how tall they are, that even though there's infinitely many of them, I'm doing it for a finite amount of time, I'm going to get some sort of answer. Cool. Over here, it turns out that in order to get an answer, in order for us to be able to evaluate what this area actually is, it turns out that we need these rectangles to kind of get small fast. And I'm going to write that down. We need these rectangles to quote unquote get small. And I'm even going to put another quotes, fast, right? What does fast even mean, right? But we need them to get small fast, all right? And I know this is kind of weird, and that, phrase may not make any sense. And so, just for the sake of providing an example without actually knowing how to do these, I'm going to provide 2 examples really quick. So the first example I'm going to have us investigate is to do the integral from 1 to infinity of 1 over x dx, okay? Now, technically, in order to execute this, we do need limits from Calculus 1, but I'm just going to wave my hand for a second and say, forget the technicalities of it, just roll with the example for a moment, because I know you can all follow this, because we're experts at antiderivatives by now, right? The antiderivative of this is going to be the natural log, technically, of the absolute value of x, but because all of our x values are positive on this particular region of integration, I'm just going to write it's the natural log of x evaluated from 1 to infinity. Now again, technically this is wrong because infinity is not quote unquote a real number. So we, technically we can't just plug this in, and we would need to use real numbers that are close to infinity, approaching infinity, which should, again, hearken to the idea of limits. But for now, I'm going to say, I'm going to allow us to just say, look, this is the natural log of infinity minus the natural log of 1. Now, the natural log of 1 is famous for being 0. And again, that's because this is the same thing as saying e raised to what power is equal to 1. And that question mark there, right? What is the answer? The answer is 0. And same thing over here, right? The natural log of infinity is the same thing as saying e raised to what power is equal to infinity. But here, that power is actually going to be infinity. So it turns out that this answer is infinite. And this integral, we say this integral, there's a special word we use because we say it diverges. And diverges simply means that we don't get a concrete numerical answer. So because here, we're getting positive infinity for the answer, there's infinite area, we're not getting a solid concrete answer, we're going to say that this integral diverges, okay? And I said I was going to provide 2 examples, so let me provide the second one really quick. Right under it, let's do the integral from 1 to infinity of 1 over x squared dx. Now, please be very careful. The antiderivative of this is not the natural log of x squared, because this is the same thing as x raised to the negative 2 power, and we can use just the good old-fashioned antiderivative rule for the power rule. So we add 1 to the exponent, divide by the new exponent. We're going to get negative 1 over x evaluated from 1 to infinity. And we're going to do the same thing where we're going to plug in infinity. Negative 1 over infinity minus this negative is going to become a plus. So plus 1 over 1, which I got from plugging in the 1 right there. Now, the question is, okay, what do we do with this 1 over infinity? Well, last time I checked, 1 over a really big number is something really tiny, right? Think of like 1 over 10, 1 over 100, 1 over 1,000, right? As this denominator gets bigger, we get, 0.1, 0.01, 0.001, and it keeps going on and eventually gets smaller and smaller. So it turns out that 1 over infinity, that's just famous for being the number 0 and negative 0, 0. So it turns out that this answer is actually equal to 1. And this, we would say that this integral, we would say converges. And we would say it converges to 1. Okay, so this word convergent or converges, if you hear, an integral converges, that means that we were able to successfully evaluate this integral and get a number out. So up to this point in this class, every integral that we've been able to actually evaluate with bounds that has real bounds like 3 to 7 and 0 to 2 and whatever, they've all been convergent, right? Every integral you've ever done that you get a number out, those are all convergent integrals. And there haven't really been too many integrals, if any at all, at this point that we've gotten infinity out or negative infinity or been unable to actually evaluate those integrals. But the reason why I'm giving these 2 examples as kind of a preliminary idea is, like I said before, this really underlines a huge Calculus 3 concept. And to illustrate my point even further, we're going to go over to our good friend Desmos, and we're going to investigate these 2 functions. And what I want you to remember is, well, actually here, let me take a screenshot so I can annotate this. What we're going to be doing is, when we're doing this, oh, is it going to let me? All right, so when we're doing this, we are calculating the area from x is equal to 1 all the way to infinity underneath this green curve, right? So the integral 1 over x dx is going to give us all of this area here. And what we found out is that if I asked you to fill this particular region with dirt, that you would need infinitely many square feet of dirt in order to fill up this entire region forever and ever and ever and ever and ever. Like that's what we would end up needing. Mathematically, we just showed that happening. Now, I did mention before that there's this idea of a graph kind of getting small quick enough, that those rectangles are not too tall. And you'll notice that if I pop in the graph of 1 over x squared, and we take a screenshot here just so I can annotate it again, right? Talking about that same region of integration, maybe I'll highlight it in with green for the green graph. So this region of integration here for the green one has way more space that we're adding up for an infinite amount of time compared to the blue one, right? The blue one like has a little space here and then it like dies out really, really, really quickly. Now, I don't mean, when I say dies out, I don't mean that it goes to zero, right? But when we zoom in here, you can kind of see that there's a ton of space underneath this green graph. Again, if the goal of the integral is that we're adding up all of this space underneath the graph, you can kind of imagine that these rectangles that we would be adding up, they all have, you know, a pretty substantially heavy height to them, that they all contribute pretty sizably to solving this integral 1 over x dx from 1 to infinity. And so this reason, this kind of brand new mathematical idea is that the function 1 over x doesn't go to zero, quote unquote, fast enough. And because this is happening, or rather because it isn't happening, these rectangles like are still very tall for a very long period of time. Whereas you'll notice that if we look at this blue graph, there's almost no space underneath this blue graph. And the idea being that if I were to zoom out and kind of go over and head off towards infinity here, you might say, hey, the green graph disappeared, right? It's no longer there. But if I zoom in, the amount of space that is underneath this green graph compared to this blue one where I would have to keep zooming just to even get a little bit. What are we at? We're at 2 times 10 to the -5th, maybe half of that for these rectangles, okay? And so comparatively, compared to the green graph, I'd have to zoom out, still zooming out. Where is it? It's right there. I can't even see, you know, the rectangles for the blue one, right? The blue rectangles are like there, and the green rectangles would be all the way up there, okay? And so all of this is just leading to this idea that when we're doing integrals, these what we call improper integrals, and the first example of an improper integral is an integral that has an infinity in the bound, whether it's the upper bound, lower bound, or both bounds. The idea is that integrals that are improper deal with this idea of, hey, is my function dying off fast enough, right? Is the gap between my function, right? There's 1 over x, and my other function, which is, you know, 1 over x squared. Granted, both these should be going up here, but whatever, right? There's 1 over x squared. Is it, quote unquote, dying out fast enough? And we saw via the math that we did that it turns out, mathematically speaking, we can kind of start to get a feel for it, which is that, yeah, if I have a graph like 1 over x squared, it dies out fast enough so that this area that I'm adding up, even though I'm going on forever and ever and ever, it turns out that it's so small that when I add up all those pieces, it perfectly equals 1. So if I was trying to fill that area with dirt, I would need 1 square foot of dirt to fully saturate all of the area underneath that blue curve from 1 to infinity. Whereas the green curve, it'd be impossible to satisfy, right? This function, 1 over x, goes to 0, right? It does, but there's so much space for such a long period of time that as we go off to infinity in the x direction, all of this space, all these rectangles that we would add up, would eventually add up to infinite area. Okay, so this might seem a little bit strange, and perhaps this is a good place to stop the first video, which is, you know, this video is just simply to serve as an introduction to improper integrals and this very strange brand new idea of convergent versus divergent integrals. And we're getting our first taste of that by investigating the integrals of 1 over x and the integral of 1 over x squared. And we just got introduced to the brand new idea that when we're talking about integrals at infinity, we are concerned with there being too much space, or that our rectangles are going to be way too big when I'm adding them up. And again, we didn't have that problem when we did finite integration, right? When we were integrating on a fixed set of bounds from A to B, we were never worried about the height of these rectangles, because there was some theory that said, aka the fundamental theorem of calculus, that said, look, I can calculate the area here, no problem. You just do the antiderivative, plug in the bounds, life is good. And we are doing something similar in terms of the algebra to get our answers for convergent and divergent. We just have like a little bit more that we have to consider. So I'm going to leave this video here, and when you feel like you've got the general idea of an introduction to improper integrals, let's pop over to the next one.